Today we are going to discuss the topic, the escape speed. Now, dear children, you might have noticed that if we throw an object vertically upwards from the surface of Earth, now this object will attain a certain height, and after attaining the certain height, now this object will return back to the Earth's surface. Now, if we go on increasing the speed or the velocity with which this object is projected vertically upwards, now this object will attain greater heights, but after attaining the certain height, this object returns back to the Earth's surface. Now, the question is it possible to throw an object with a certain speed such that it just escapes the gravitational field of the Earth? The answer is yes. If we throw an object with a certain speed, minimum speed, now such that this object overcomes the gravitational field of Earth. By this term we mean if we throw an object with a certain minimum speed such that the gravitational field of Earth has no effect on it, then we say that simply this object has escaped the Earth's surface. Now, the escape speed from a point or from the surface of Earth is defined as the minimum speed with which a body or a projectile must be projected from the point so that it just escape the gravitational field produced by the massive body like Earth. I will repeat the definition. The escape speed from a point is defined as a minimum speed with which the body must be projected, body of certain mass must be projected so that it just overcomes the gravitational field of Earth and never returns back on its own, is known as the escape speed. Now, for Earth, the escape speed is 11.2 kilometer per second. That means if we throw an object with a speed of 11.2 kilometer per second from the Earth's surface, then the object will escape. The gravitational field of Earth has no effect on it. Now, this is the escape speed of Earth. Now, later we will see this escape speed depends on the mass from the gravitational field of which the body has to escape. It depends on its size, but is independent of the mass of the body which has to escape the gravitational field of Earth or a certain massive body, and it is also independent of the angle of the projection. Now, let me derive the expression for the escape speed. Now, let me calculate the escape speed, derive an expression for the escape speed from a point on the Earth's surface. Now, let me take the mass of the body, mass of a body which has to escape from the surface of Earth. This has small m. Now, to calculate the escape speed from a point on the surface of Earth, we make certain assumptions. Now, these assumptions are: number one assumption is there is no other body other than the earth, which will exert the force on the mass m. By this statement we mean there must be no body other than the earth and this body of mass m, which will experience the force on mass small m. Implies, apart from earth, there must be no other body which will exert the force on this small mass. This is first assumption. Now, second assumption is the projectile just escapes the gravitational field of earth. It escapes the earth's gravity. That is, it stops after reaching an infinite distance from the earth. Now I will repeat. Second assumption is the projectile just escapes the gravitational field of earth. By this statement we mean the projectile or a body stops after reaching an infinite distance from the earth. This is second assumption. Therefore, from this statement we can conclude, if a body stops after reaching an infinite distance from the surface of earth, then we can take its mechanical energy as 0. Now, third assumption is the air resistance is neglected. These are the assumptions which we need to make while deriving the expression for the escape speed. Since the gravitational force is conservative in nature, therefore the mechanical energy of mass m, this small m, is conserved when mass m is thrown with an escape speed ve. I will write this. Since gravitational force is conservative in nature, therefore the mechanical energy is conserved when a projectile or a body of mass m is thrown with the escape speed. At infinite distance from the surface of earth, the mass stops and hence its kinetic energy will be 0. Now, you might be knowing that at infinite distance from the surface of earth, the gravitational potential energy becomes also 0. Let me write, at the surface of earth, at the surface of earth, mechanical energy E is given by EI, Now, EI is equal to, now the sum total of the kinetic energy and the gravitational potential energy. Now, since kinetic energy can be written as half of mve square, where m is the mass of the body which has to escape the gravitational field of earth, and ve stands for the escape speed. Now, plus. Now, in last lecture, we have derived the expression for the gravitational potential energy on the earth's surface. That gravitational potential energy on the earth's surface is given by minus gmm by r square. Now, if we talk of the surface of earth, then I can write the gravitational potential energy as minus G. Now ME stands for the mass of Earth. Small m is the mass of the body, and divided by, since we are talking of the total mechanical energy at the surface of Earth, therefore this R is to be replaced by small r, is to be replaced by RE square. Now we can write this expression as half of m VE square, then this can be written as minus G ME m by RE square. This is the total mechanical energy EI at the Earth's surface. Now, at infinity, as I have already discussed with you, as at infinity, the mechanical energy is 0. That is EF equals 0. Because we make an assumption that the body has to just escape the gravitational field of Earth. That means it stops after reaching an infinite distance from the Earth's surface. If it stops, its kinetic energy can be treated as 0, and the gravitational potential energy, instead of R, we need to write infinity, because gravitational potential energy at infinity, that is 0, which in last lecture we call this as the level of zero potential energy. Now the kinetic energy will be 0 on account of its speed, and the gravitational potential energy of a body at infinity is also 0. Therefore, we can write EF is equal to 0. Now, as per the conservation of mechanical energy, we can write EI is equal to EF. As per conservation of mechanical energy, EI equals EF. Now since EI is equal to half of m V square, then minus G ME small m by RE square, and this must be equivalent to 0. Now this is the statement as per the conservation of mechanical energy, or we can write this as half of m V square is equal to G ME m by RE square. Now this m and m cancels. Therefore, we are left with VE square is equal to, now this will be twice G ME by RE square. ME by RE square. Now see, this gravitational potential energy is minus G mm, not R square, this is R. So instead of R we can write, so let me neglect the square needs to be neglected. because we have the expression for gravitational potential energy as minus g mm by r. On the Earth's surface, small r is to be replaced by Re. And we are left with Ve equals under root of twice g me by Re. This is the required expression for the escape speed. Now, mark this as equation 1. Now, this is the expression for escape speed in terms of the mass and the radius, means size. If rho e equals density of earth, then I can write density as mass per unit volume. I will write Re cube here, I will write Re, since the earth is treated as the sphere. Therefore, Me equals 4 by 3 pi Re cube into rho e. Now, instead of Me in equation 1, let me write 4 by 3 pi Re cube rho e. Therefore, equation first reduces to Ve is equal to under root of, this is twice g, this is Re. Now, instead of m, let me write 4 by 3 pi Re cube rho e. Now, let me simplify this, and we can write this as, this is 8 pi g rho e, and we have Re by 3. This is the expression for the escape speed in terms of the density and the radius of Earth. Now, if we analyze these two equations, we find that escape speed depends on number 1 is the mass of the earth, mass of earth, and second one is the radius of earth. Now, from this equation, we have V varies as Re rather than the square root of Re, and density, which in turn depends on the mass. But independent of escape speed is independent of number 1, mass of the body. I will write mass m of a body, and number 2, Now, angle of projection. Angle of projection. Escape speed is independent of mass of body and the angle of projection, but simply depends on the mass, we call the density, and the size or the radius of the earth. Now another expression in terms of the escape speed. In this expression, if we have small g equals gm by re square. This is the expression for the acceleration due to gravity. Now, if we write this as gme equals g times re square, therefore, equation first becomes ve equals under root of, this is 2 by re into gme can be replaced by gre square. Now, simplifying this equation, we are left with ve is equal to, so this will be under root of 2 gre. This is another expression for escape speed. Again, independent of the mass of the body, depends on the size. Now for Earth. For Earth, V is equal to twice, G is 9.8, or to simplify the calculations, you can treat this as 10, and radius of Earth is 6.4 into 10 raised to power 6 meters. Now, on simplifying this, we are left with the value which is 11.2 kilometer per second, which is the value of escape speed of Earth. If an object has to escape the gravitational field of Earth, the minimum velocity with which this object has to be projected, that is 11.2 kilometer per second. Now, this is all about the escape speed. Now, you can write the question. The question is like this. You can write Jupiter has a mass 318 times the mass of Earth, 18 times the mass of Earth, and its radius is 11.2 times the Earth. 11.2 times the Earth. 2 times the Earth. Estimate the escape velocity of a body. Estimate escape velocity of a body from the Jupiter surface. Now, given is escape velocity escape velocity from the Earth's surface is equal to 11.2 kilometer per second. Is this the question? Let me write down its data. Jupiter has a mass 318 times the mass of Earth. I will write mg as mass of Jupiter, which is 318 times the mass of Earth. And another condition is, and its radius is 11.2 times the Earth's radius. So I can write radius of Jupiter is equal to 11.2 times the radius of Earth. Now, the escape speed of Earth in terms of mass and radius can be written as twice g me by re. And similarly, for the Jupiter, I can write Vj equals, this is twice g mj divided by rg. Now, let me divide these two equations. I can write Vj by Ve is equal to, now I can write this equation as, this is twice g mj rj, then whole divided by under root of twice g me by re. But I can write this as re divided by twice g me. This 2g and 2g cancels. Now mj can be written as, now I can write this as Vj by Ve equals twice g and twice g cancels. Then we have mj. Mj can be written as 318 times the mass of Earth, and Rj can be written as 11.2 times the radius of Earth into, we have Re divided by Me. Re by Me. This Me cancels the Me, Re cancels with Re. Therefore, you are left with Vj equals Ve times under root of 318 by 11.2. Now, on substituting Ve equals 11.2 kilometer per second, we are left with Vj as 59.71. 59.71 kilometer per second. This is the required value for the escape speed for the, what we call as, for the Jupiter. Now this is all about the escape speed. Now let me take the another topic, Very simple, orbital speed. Now, you know that the satellite is an object which is revolving around the planet. Here, if we talk of the Earth, therefore satellite is an object which is revolving around the Earth. Now, we also know that this satellite which is orbiting around the Earth or any planet is bound to the Earth by the gravitational force, by the gravitational attraction. For example, Moon is a natural satellite of Earth. So, Jupiter on the other hand is known to possess 16 such natural satellites. Now, this Moon keeps on revolving in its own orbit around the Earth because of the gravitational force exerted by the Earth on the Moon, and the speed which is required to, now the speed which is required to put a given satellite into a given orbit around the Earth's surface is known as the orbital speed. You can write orbital speed is the speed required to put the satellite into given orbit around the Earth's surface. Around the Earth's surface. There is a definition for the orbital speed. Let me calculate its expression. And we treat this as the Earth, this as Earth. Let me write the parameters as mass of Earth, this is m, width center O. Now, radius of Earth is r. Suppose the satellite is revolving around the Earth in the circular path. This is the path along which the satellite of mass m is revolving. I will write mass of satellite as small m. Now let h be the height of satellite from above the reference level, from above the Earth's surface. I will write height of satellite from Earth's surface. From Earth's surface. Let me write this as h. Therefore, radius of orbit of satellite let me represent this with small r. Therefore, this small r can be written as capital R, radius of Earth plus height of satellite from above the Earth's surface. Now see, since the satellite in a particular orbit is moving with the constant speed, Now you know that its velocity is changing on account of the change in the direction. Therefore, the gravitational force or the gravitational force which the Earth will experience on this satellite, that gravitational force between Earth and satellite, that gravitational force is given by F equals G, capital M, mass of Earth, mass of satellite divided by the R plus H ka whole square, because we need to take the distance from the center of Earth to the satellite. Now this is the expression for the gravitational force between Earth and satellite. Now in previous classes you might have read about the centripetal force. Centripetal force is a type of force on account of which the particle keeps on revolving in a circular path, along a path other than the straight line path. Now, if we talk of the atom, nucleus, now the electrons are revolving around the nucleus in their respective shells. Now, you also know that nucleus is positively charged, and the electrons which are revolving around the nucleus being negatively charged. Now, in this case, the electrons require the centripetal force on account of which these electrons will keep on revolving in their particular shell. Now, in this case, that centripetal force is provided by the force of attraction between the nucleus and the electron. Similarly, in case of the Earth satellite system, now this satellite is revolving around the Earth in its own orbit, and in this case, in case of Earth-Moon system, Earth satellite system, the gravitational force or the centripetal force is provided by the gravitational force between the Earth and the satellite. Therefore, we can write centripetal force and this centripetal force is equal to m v square by, actually small r, but small r equals r plus h. This is a centripetal force on account of which the satellite of mass small m keeps on revolving in its path, along its path. Now, this centripetal force is provided by the gravitational force between the Earth and the satellite. Therefore, we can write mv square divided by r plus h is equal to g capital M small m divided by r plus h ka square. Now m and m cancels, one r plus h cancels with r plus h. We are left with, this is v square equals, this is g times m divided by r plus h. Or we can write this as v equals under root of gm divided by r plus h. which is the expression for the orbital speed. Rather than this equation gives the orbital speed of a satellite of mass small m revolving around the Earth in a circular orbit of radius r. Now, if the satellite is orbiting, this is a special case, Now, if satellite is orbiting very close to Earth, then we can write r plus h as approximately equivalent to r, because the height will be far less than the radius. Therefore, with this substitution, the escape speed comes out to be under root of gm by r. This equation gives the orbital speed if the satellite is orbiting very close to the Earth. Acceleration due to gravity is given by gm by r square, implies gm comes out to be gr square. Therefore, v equals, instead of gm I can write gr square by r. 1 r cancels, we are left with gr. This is the orbital speed of a satellite which is orbiting very close to the Earth. On putting the values of g and r, we are left with this is 7.92 kilometer per second. This is the orbital speed of the satellite which is orbiting very close to the Earth. Now, from this expression, we conclude that the orbital speed depends on the mass of the Earth and the radius, but is independent of the mass of the satellite. This is all about the orbital speed. Now, one more important point, now which you can write as we have escape speed under root of twice gr, and we have the orbital speed, let me write, this is under root of gr. Now, v by vu, dividing these two equations, we are left with root 2. Where escape speed is root 2 times the orbital speed. This equation is an important equation. Yes, this is all about today's lecture.